Welcome to the topic of isocontours. Today I'm going to talk about the computation algorithm for isocontour generations. So what is an isocontour? An isocontour is a collection of points in a scalar field that have a constant value. So if you have a two-dimensional scalar field, the isocontour is isoline. They are curves. If the scalar field is defined in three-dimensional space, the isocontour gives you something called isosurface. Sometimes people also call isocontour as level set. So the equation at the bottom is the definition. Level set or isocontour C are a collection of points x where the scalar function f of x equal to c, and c is a constant. If you change the constant value c, you're going to receive different isocontours. How do you compute isocontour from a two-dimensional scalar field? The algorithm is actually pretty straightforward. So let's focus on two-dimensional regular Cartesian mesh. Here we have a collection of grid points, and every 4 grid points form a square cell. Assuming you specify the iso value, that is a contour constant value as c, you can immediately go through the points and identify points that have value greater than the iso value c, and also points that have value less than isocontour c. To simplify our explanation, we'll assume there's no point that have value equal to c. In the diagram here, the black points have value greater than c, and the white point have value less than c. Now, we are going to compute isocontour cell by cell. So that is, you look at each cell. If some of the points on the square cell are greater than the iso value, and some of the points are less than iso value, if we assume the scalar field, the scalar value change linearly within a cell, you can be sure that there is a isocontour cutting through the cell. In the example here, you see a red line cutting through a cell. The top half of the cell have grid points that have value greater than the iso value, and the bottom edge of the cell have 2 grid points that have value lower than them. You can focus on edge by edge. You will see 2 vertical edge have 0 crossing. That is because if value change linearly from white to black cell, you can be sure that there's a point on the edge that have value equal to the iso value. So you figured out the intersection, that is a 0 crossing, where the point on the vertical edge that have value exactly equal to the iso value, and then you connect those 2 points by the red line here. And you proceed to the next cell that also have grid point whose value is greater than the iso value and smaller than the iso value, then you compute. Then you proceed from cell by cell, you connect all the intersection points together, and you form a complete isocontour in this example. Computing isocontour in a cell is an inverse problem compared to value interpolation. This is what I mean. Assume you have a square cell that have 4 corners, P0, P1, P2, and P3. Also, assuming along 2 vertical edges, you interpolate the value of P4 and P5. Now, if you want to know the value of P, the red dot here, you can simply interpolate the values from P4 and P5 using the linear interpolation function that we discussed in one of our previous lectures. To get isocontour that contain point P, where the function value P equal to a constant C, what you need to do is you need to find all the possible points within this square that has value C. If you assume the value change within the cell linearly, then you are trying to solve an inverse linear interpolation problem. That is, instead of finding a value for a given point in P, now you have value C, you want to find those points that have value equal to C. So now let me explain how do you do it. First of all, given the iso value in the cell, you compare the value at each of the vertices with the iso value C. If it's greater than the iso value, in this example here, I mark as black dot and with a plus sign. If the value at the corner is lower than the iso value, then here I mark as a white circle and also with a minus sign. Because we assume the value changes linearly within the cell, any edge that has zero crossing, that is, the two vertices of the edge have both negative and a positive sign, and you know there must be a point on the edge that has value equal to the ISO value C. So this is what I mean by zero crossing. Because you know the values at two endpoints of the edge, so you can actually calculate where on the edge the point will have value equal to C. I'm going to show you how to get this point through the principle of linear interpolation. In the example here, two vertical edges have zero crossing, and I apply the principle of linear interpolation, get the intersection point, that is the zero crossing. Then I simply connect the points by a line, and this line represents all the points that have a constant value equal to C. Now let's take a closer look at each of the steps. First of all is that we want to identify edges that have zero crossing. This is based on the principle of linear interpolation. Assuming two endpoints on the edge, V1 the value of the P1 and V2 which is the value of the P2. Assuming one is greater than the ISO value C, here I use the black dot, and the other is lower than the ISO value, depicted as the white circle. On the left of this slide, I plot the function value of P1 and P2, where the x-axis is the position and the y-axis is the function value. We assume values are changing linearly along the edge, so this is why I draw a red line between those two dots. Now, because the black dot has greater value than C and the white dot has smaller value than C, so you can imagine that you can draw a line, blue line here, that's where the C value will intersect the red line. We can base on this linear proportional principle, so we can actually infer the position of the P that has function value C on the edge, which I show on the right-hand side of this image. So how do we calculate position P? Again, this is based on the proportional principle due to the value change linearly along the edge. So assuming the P, the position that is unknown, the distance of P to the left edge, that is the P1, is D1. And the distance of P to the right point, P2, is D2. Then we have a ratio that is D1 over D2 equal to the value between V1 and C divided by C and V2. That is over here. So from here, we can further derive what is the distance D1, that is P minus P1. Here I use boldface representing P and P1, P2 are all positional vectors. That would be 2 dimensions or 3 dimensions. Here I just assume it's 2 dimensions. P minus P1 is the distance D1 divided by P2 minus P1, that is the distance D2, equal to V1 minus C divided by V1 minus V2. So from here, we can actually solve the position P by shifting the terms around in this equation, and we get this answer in the gray color box. So the third step is connecting the intersection points. This is because we assume all the values changes linearly along the edge in the cell, or any edge in the cell. So if we have two blue circles that we know they have value equal to the ISO value C, if you draw a line that connects those 2 points, every point along the blue line will have the same value C. So this gives us a portion of the isocontour within the cell. Now you just repeat step 1 through step 3 I just mentioned for every single cell, then you are going to get the isocontour piece by piece throughout the domain. You might ask, how many ways can isocontour intersect a linear rectangular cell? Let's look at together. Each cell, if it's a rectangle, has 4 vertices, and the value at every vertex can be either greater or less than the contour value. If you place the 4 vertices together, represent each vertex as a bit, mark the bit 1 if the value is greater than isocontour value C, and put a 0 if it's less than the value C. As you can see, there are 4 bits, and each bit can take either 0 or 1, so there will be total 2 times 2 times 2 times 2 equals to 16 cases. Here, let me show you all the different cases. As before, the white circle represents vertices that have value less than contour value C, and the black dot represent value greater than isocontour C. If you actually compute the contour within each of the cells, you're going to realize that there are only 4 unique topological cases. That is, we don't consider the position of the contour within a cell. We only consider how the contour is intersecting the cell. The first case is that the contour actually does not intersect with the cell. Then we have another case, the contour cuts through one corner of the cell. This actually can be mapped to 4 different cases because the contour can cut each of the corners, and there are 4 corners. But because we are not concerned with the position, so they are all the same. One case, that is, the contour only cut through one corner of the cell. And then we have a case of the contour cut through 2 edges, that is, divide the cell into one side that have value lower than the contour value and the other side that have value greater than the contour values. And finally, there's a more complex case, that is, there can be 2 contours going through the cell and each cut through one corner. And again, you can imagine because there are 2 pair of the corner that's possible, so they are corresponding to 2 different cases, but they look the same topologically speaking. So I want you to think about, for each case here, topological cases here, what are the possible bit strings mapped to the cases. So now let's put everything together. So this is our isocontouring algorithm for 2D cell. First of all, your program is going to have a loop that will process one cell at a time. And then for each cell, you're going to compare the values at the vertices with the contour value C. This is to identify the edges that have 0 crossing. That is, the isocontour is going to cut through the edges. And then you perform linear interpolation to find out the exact location that the isocontour intersects the edges. And finally, you connect the interpolated position together by straight lines. So now let's see how can we extend the 2D isocontour algorithm to 3-dimensional data. So in this case, we are going to compute surface, and we typically call that isosurfaces. The 3-dimensional algorithm is very similar to the 2D algorithm we just described, except that now we are dealing with 3-dimensional cells, for example, cube or tetrahedra. What we are going to do is to still compare the values at the vertices of each edge and determine what edge will have intersection with isosurface. This is done by checking whether one vertex has value larger than the iso value and the other vertex has value lower than the isocontour value. And any cells that have isosurface intersect with it, we call that active cells. Once we identify the active cells and also the edges that have intersection, we're going to compute the intersection and also triangulate the section to create surface patches. And the patches are computed cell by cell, all together form a isosurface. Now let's look at the case of tetrahedral cells. We have 4 vertices and also 4 faces. Because we are assuming the values of the field change linearly within the cell, for a given cell, if the minimum value among the 4 vertices is lower than the iso value, and the maximum value among the 4 vertices is greater than the iso contour values, then this cell is for sure to contain part of the isosurface. And we can mark the vertices by plus or minus signs. Because for a tetrahedral cell, there are 4 vertices, and each vertex can have plus or minus sign. So there are total 2 to the power of 4 equals to 16 combinations describe the geometry of the isosurface patch within the cell. But actually, I'm going to show you that there will be only 3 unique topological cases. So the first case is that the isosurface does not intersect with the cell. So that means all the four vertices have values either greater than the isocontour value or smaller than the isocontour values. Sometimes the convention is that for value greater than the isocontour value, we call those cells outside the isosurface. And for the vertices that have value lower than the isocontour value, we call those cells inside of the isosurface. So the second case is that the isosurface cut through the tetrahedral cell by one corner. This corresponds to two possible geometric cases. Here on the left, we have one vertex that has value greater than the isocontour value, and the other three vertices have value less than the isocontour value. And the case on the right, we have one vertex whose value is lower than the isocontour value, and the other three vertices have value greater than the isocontour value. And remember our inside-outside convention. So here we say in the case on the left, one vertex is outside, three vertex are inside. And the case on the right, one vertex is inside the isosurface and three vertices are outside the isosurface. Now, if you ask what edges have intersection with the isosurface, what you need to do is look for edges that have zero crossing. Again, edges whose two endpoints have values both greater and smaller than the isocontour values. So here, the blue edges are those edges. Each of the blue edges has one black vertex and one white vertex. So how do you compute the intersection point on the active edges? Based on the value on the black and the white dot, and we apply the same linear interpolation principle like we discussed in the 2D case and find out the position of the intersection shown as a red dot here. After we get the intersection points, we connect them to form in this case, a single triangle. So the next case is that we have two vertices that are outside of the isosurface and the other two are inside. So you can see that we have four active edges here, and we can apply linear interpolation to find out the intersection points shown in red here. After that, because we have 4 points, we are going to use two triangles to connect those 4 points, and those two triangles are the isosurface patches within this current cell. Now let's put the algorithm all together for three-dimensional tetrahedral cells. It's the same principle as the 2D algorithm. Essentially, we are going through cell by cell, compare the values at the 4 corners, and then we find out the active edges for cells that are active cells. From the intersection points on the active edges, we can connect them to one or two triangles. After you are done with triangulation for the current cell, you move on to the next cell, and so on and so forth. So now let's look at how do we compute isosurface from rectangular cells. And the algorithm I'm going to talk about is the famous Marching Cubes algorithm. For rectangular cell, there are A vertices at the corners, and because each vertex can have value greater or smaller than the iso value, so we have 2 to the power A equal to 256 different cases. This is the different geometric cases how an isosurface can intersect with a cubic cell. Here I just show different cases, and the cases are based on how the values are distributed over the A corners. But what I'm going to show you is that the total number of unique topological cases is much smaller than 256. For example, if you consider value symmetry, what does that mean? So over here, we have a plus and minus signs put on the vertices, indicating whether their values are greater or smaller than the iso value. But if you just simply flip the sign, that is, you change every plus sign to minus sign, you are actually going to get the same set of active edges. In terms of the topology of the surface patch, they will be the same, because you're going to get the same intersection points, and then we are going to connect those points in the same way. So this is what we call value symmetry. From the 256 cases, you can find multiple cases that belong to this value symmetry, and topologically speaking, they can be represented by a single case. Then another thing you can consider is we call rotation symmetry. What do I mean here? In the example here, you will see This is one way the isocontour can intersect with the cell. If you rotate this cube, that is, you keep the signs on the vertices, but you simply rotate it. So here I rotated counterclockwise from the top by 90 degrees. So for the surface patch now, after rotation, you have different positions, but if you look at it, it's the same topology. So out of those 256 cases, you're going to find out, again, multiple cases belong to this rotation symmetry, and they can be represented by a single case. So if you go through all the 256 cases and identify value symmetry and the rotation symmetry, etc., you can reduce the cases down to 15. And this is what the famous marching cubes algorithm discovered. Here I show all the 15 unique topological cases for isosurface intersections through a cube. So now let's look at the implementation of marching cubes algorithm a little bit. This was proposed originally by Lorenzen and Klein in 1987. For a cubic cell, we have 8 vertices. So you can create a 8-bit number as shown at the bottom of this slide. Each vertex is represented by the bit in this number. So the corresponding bit has a value 1 if the value at the vertex is greater than the isocontour value C, and its value 0 is less than the value C. This is similar to what we have already described before for 2D case. With this 8 bits index number, every cell based on the value defined at the vertices will have an index map to a range between 0 and 255. And from the 0 to 255, you can create a table. The tables here shows 15 different topological cases for each intersection. It indicates that where are the active edges, that is, edges that intersect by the isosurface. So you can reduce from the 255 cases down to these 15 cases and then perform a table lookup. You only need to focus on the active edges provided in the table to perform interpolation. And also, each of the cases in the original marching cubes paper provides how you can triangulate the resulting points. The points on the active edges are computed using linear interpolation based on the same method we discussed in 2D and the 3D tetrahedral case. After you have the point, you connect them together. So why is it called marching cubes? This is because you are going to visit the data cell by cell and evaluate the case index for each cell and perform triangulation. After you finish the current cell, you can march to the next cell because the adjacent cells share edges. So you can save your effort to perform interpolations on the edges that are shared by the cell that you have already processed. So you march along these cells and you perform the same process. Okay, so this is the isosurface algorithm for 3-dimensional regular data called marching cubes algorithm. And this concludes the topic of computing isosurface from 2D and 3D data.